All right. Okay, so you guys ready to start? We're going to work in Maple today, and we're actually going to work with the actual program today. No, we are going to work with the program. Because you know how on Tuesday we did it by hand, right? Yes. So, I kind of deviated from what I did last time I taught this class, so I thought I kind of wanted to stay in line with the book more. So I was attempting to, or I thought I would show you how you could do some of these problems, your homework problems, with Maple. Okay, so we're going to do the homework problems in 5.3, and we're going to do them with Maple and see how you could solve these problems using Maple. Okay, and see if you guys can figure out some of them. All right. So if we look at problem 1 in chapter 5.3, it says find f of 1, f of 2, and f of 3, and f of 4 if f of n is defined recursively by f of 0 equals 1, and for n equals 0, 1, 2, on up to infinity. All right. And then we have a through d. And so did any of you actually attempt to solve these problems with your computer, or did you all do them by hand? Oh, actually, Peter did. Yeah. Todd, did you?
No, I don't.
Oh, yeah. Okay. And you solved them? Awesome. Okay, good. Well, hopefully this isn't too boring for you. All right. So these types of problems are actually solved by Maple pretty well. Okay. So let's see how we could write. I'm going to do A and D, and then you guys are going to do B and C. Okay? So I'm going to show you how you can do A and D, and then you guys can do B and C. All right. So letter A.
The chapter 5 equation assignment says it's D equals 6, but here it says it's D plus 1.
Oh, it is due after a break. So if I put the wrong date that it's due, I will change it. Thanks, Todd. Yeah, and then at the end of class, if we have time, we can work on that assignment as well. All right? But let's look at letter A here. It says f of n plus 1 equals f of n plus 2. All right. So when you're doing these types of problems, you want to kind of do them recursively. Well, if you do want to do them recursively. And so in order to do them recursively, you have to make your function look like this and not f of n plus 1. So what's another way that we could write the right-hand side of our equation if we change the left-hand side of our equation to f of n? Yes, you do n minus 1. Okay? Okay, so that's how we're going to kind of change these so that we can write them inside of our computer. Because remember, when we do recursion, if this is our input, and our input's base case is f of 0 equals 1, we know that n has to get smaller. We know that this parameter has to get smaller so that it can reach its base case. So it makes sense that this would be n minus 1, okay, and not just n. Otherwise, we're never going to reach our base case. Okay, so you can kind of think of it that way as well, all right? Or you can think of it that we're changing this to f of n so that we can figure out f of n. So then if this was n plus 1, then this f of n is n minus 1. He's 1 below n. Okay? All right. So if you're going to write this in Maple, we could actually write this without writing a full-blown procedure. Okay? You guys can follow along with me if you want. Now, I named these after the exercises. So this was exercise 1A. All right. And actually, in the documentation, they go over how you can write these. It acts like a procedure, but you don't have to write the whole procedural syntax when you're writing these. Okay. So that's how you would write it out. Okay. You would say this procedure, exercise 1A, is assigned the value of n going into the function exercise 1a, notice that that's its recursive call. Okay, and in its recursive call, it's sending its it's sending n in minus 1. Okay. Notice that we have not put in the base case yet, so this would be an infinite recursive call. If we called it right now, it would do Stack Overflow. It would give us a big red error. Okay. So we enter in our exercise 1a procedure, and then we put in our base case. And what Maple does is it creates a table for you of your base cases that you insert. Okay. So we're saying when n is 0, then our output should be 1. Okay. And so that creates the base case for us. And now we can give it a sequence of numbers. We could give it one number at a time. So like if we wanted to test it for 2, it does give us 5. And if you look at your answers and you look at your answers in the book, or you just plug in n equals 2, you do get the answer of 5. All right. But of course, there's an easier way to kind of insert our input using our sequence command. Okay. All right. So maybe I'll just write out our sequence command. So you would put your exercise or your procedure call, okay, and you'd give it that value, and then you tell it what values of I you want to insert inside of this procedure. And they wanted you to find f of 1, 2, 3, and 4. So we'll say from 1 to 4. And that will actually give you your output of 3, 5, 7, and 9, which if you look in the back of your book, those are the answers. And if you plug in n, or you figured them out by hand, those were your answers. Okay? So not too hard. A little extra typing, and then you don't have to figure out all those answers by hand, right? Which is what a computer is best at. All right. Let's try letter D. Okay, so we have a function that looks like this. It's a recursive function. So again, we're going to change f of n plus 1 to just f of n. And so then on the right-hand side, you would change it to n minus 1, right? And it was plus f of n minus 1, and then plus 1. So not too hard. Okay. Just have to remember your syntax to raise something to a power. All right, so this is letter D. And do properly label them, because you guys are going to turn this in. So you can shorten the word exercise if you want to, but do properly label them. All right. So then we do our same syntax. All right. So then we would have our n minus 1 to the power of 2 plus our n minus 1, and then adding to it, what was it, 1. Okay, importantly, we have to put our base case in. So you put your base case. It has the same base case, I believe. Yes. Of f of 0 equals 1. That's given to us. And then you can use your sequence command again. And of course, we'll change this letter to D. And then we find our answers. Pretty convenient. All right, so my idea was that you guys would be responsible for B and C. So I'm going to give you guys a couple minutes to do B and C. And if you finish early, think how you would do the next one. We're going to go on to number 3 here. So I'm going to give you like a couple minutes, and then if you don't finish, you'll have to finish at the end of class. But I was going to give everyone a couple minutes to kind of see if they could hash that out. Okay. In fact, I'll come walk around. I'll put this on pause. It's all good. All right. So now we can give it some input, give it a sequence. And they had some different test cases in number 3. They wanted to test for 2, 3, 4, and 5. Okay. All right. And if we check our answers in the back of our book, those should be our answers. I don't know if I checked these ones, but they should be that. You guys can look them up. All right. So, starting to get easier, I hope. Yes? All right, so how would you do letter D? So same kind of idea. Let's look at letter D. It says, okay, your function of n plus 1 equals function, or f of n minus 1 divided by f of n. So we just want to change those n's to n minus 1s on the right-hand side. So let's see here. It would be n inside of our function of n minus 1 divided by this would be n minus 2 then, and then this one would be n minus 1. Because n minus 1 minus 1 is, of course, n minus 2. And then our bottom function, our f of n, would then become f of n minus 1. We then have to give it the same base cases. So that's the important part. And then call our sequence. And of course, call it for 3D. All right. So then you guys are going to try out B and C. So you guys are responsible for hashing out or hacking out B and C. Dun, dun, dun. I'll give you a couple minutes to do that, and then when you're done, think how you would do number 5 using Maple. Oh, and let me turn on my magnifier. There he is. Cool. Okay. Actually, I have to turn this off. This is kind of annoying. Resume. And then magnify him again. All right. Okay. Determine whether each of these proposed definitions is a valid recursive definition of a function f from the set of non-negative integers to the set of integers. If f is well defined, find a formula for f of n where n is a non-negative integer and prove that your formula is valid. So it gives you a base case. It gives you that function. And then it tells you for n greater than 1. So how would you use Maple to solve this guy? First off, how would you tell if it's valid or non-valid? Yeah, it is invalid, but how would you tell that in Maple? Like, how would you use Maple to prove that that's invalid? Huh? Yeah, when you do n minus 2, what happened?
You'll get a function with attached to
Actually, did you guys figure out why A was invalid? In the back of your book, it just says invalid. Right? But did you guys figure out why it's invalid? It's very obvious when you write this in Maple why he's invalid. Yeah.
No, because it's invalid because f of n 1 is going to end up as f of 2 times f of n minus 2. But since there's no f of n, since there's no f of negative 1, it is invalid. It's a domain error. There's no negative, right? You have 1 minus 2 would be negative 1.
It's an infinite recursion because your base case is never reached with some values. So when you give it a 1, what happens?
It'll look for 2 times f of negative 1, which doesn't exist.
Yeah. Exactly. It doesn't exist, and well, even if you describe this, let's say you describe it in, well, if you write this function in Maple, it does fail. Okay, and it's because, yes, there is no base case that can be reached when you plug in that 1. Okay, so for certain values, there is no base case. So it would lead to infinite recursion. Okay, like if n is constantly going up, it's 1, 2. Sometimes he would not end. Okay. All right. So if you wanted to prove this was invalid in Maple, just write this function. In fact, we could write this function just as we were writing our functions before. We'll give it this base case, or these two base case, or this base case, and then we'll do a sequence of just a few numbers, and you could see that when it is an invalid function, Maple will tell us that it is invalid too. Okay. So let's go ahead and write him, and then you can move on to B actually too. So let's go ahead and write him out. So our function is 2 times f of n. Now notice that we don't have to convert him to n minus 1 because it's already f of n on this side. Okay. So we don't have to subtract 1 again. So it'll just be 2 times our function, our f of n minus 2. All right. So this will be number 5a. So if we were to do this in the same kind of methodology that we were using before, let's see, it would be exercise 2 times n minus 2. So notice that he doesn't know anything is wrong at first because he doesn't know that we're going to put in the wrong base case. So this will be our base case, f of 0 equals 0. So we put in our base case the same way. And then we can try to do our sequence. And we can start at 1, because that's what they said, non-negative integers. In fact, if you actually write a procedure for this, and then you run him for values of n, he goes infinitely. When you get things like this, too many levels of recursion, that means you've run out of memory. That means you've called your function way too many times. Okay.
So if we stuck more memory in the computer,
It would still run out of memory. If you had infinite memory, well, he'd run infinite time, right? So he never reaches his base case. Because his base case is never reached, we have infinite recursion. We have a recursive call that never stops calling itself. Okay? So when you have infinite recursion, then that's invalid. Okay? So that's how you kind of could have tested it in Maple. Kind of checked yourself. All right. How would you solve letter B then? You could solve letter B with the same kind of methodology. Okay. Now it says if f is a well-defined, or f is well-defined, find a formula for f of n when n is a non-negative integer and prove that your formula is valid. Okay, so let's try it. So you try putting this guy into Maple. So our function is f of n minus 1 minus 1. And our base case is f of 0 equals 1. All right. So try out letter B. And we're just kind of following the same idea we did before. Okay, and then we put in our base case, of course. F of 0 is 1. And then we can put in our sequence. And then how does writing out our sequence help us figure out what our new function would be? Yeah, the same way you probably did it in your homework, right? Hopefully. You started plugging in numbers, and then you'll see a pattern that appears. And when you look at that pattern, then you can figure out something about your function. So how did you guys change that function? So when we gave it a 1, it gave us back a 0. When we gave it a 2, it gave us back a negative 1. When we gave it a 3, it gave us back negative 2. Do you guys remember this one in your homework? When we gave it a 5, it gave us back negative 4. What would be another way that we could write that function? That's what they're asking for.
Another way to write it back like negative?
No, another way to write f of n minus 1 minus 1.
Oh.
So they asked you in the problem, if f is a well-defined, find a formula for f of n when n is a non-negative integer and prove that your formula is valid.
It would be 1. Yeah, it would be
That's right. You're on the right track.
something minus x. 1 minus n or n?
1 minus n, yes. So when you look at this pattern, okay, so when our input, when our n is 1, it's 0. When it's 2, it's negative 1. When it's 3, it's negative 2. When it's 4, it's negative 3. When it's 5, when our input's 5, our output's negative 4. Okay. So they're saying, okay, well, what's another way to kind of write that? And they said there's multiple answers. I think this problem, they said, yeah, there could be multiple answers in this problem. So another way that you could write it would be, let's see, it'd be 1 minus f of n, right? Oh, wait, did I write that wrong? No, that's right? I think that's right. Yeah. Wait, did I write that right? Wait, did I write that? I forgot my book. I'd have to look up the answer. Well, how would you prove that in Maple? So let's say we thought it was that. Let's just say, hey, we think it's that. That looks like a good answer. How would you prove that in Maple then, that these are the same? Prove that your formula is valid. What's one way that you could prove it in Maple? Yeah, you could do your k plus 1. Okay. Or you just plug this function into Maple and see if you get the same output. It's another way that you could do it. If you get the same output, then hey, then it's the same. Not for all integers, but for as much as we wanted to do it. Maybe this isn't the best way to do this, but. So what would this be? This would be part 2. So you could assign it the value of, so we can follow our same methodology here. Oh, wait. Yes. Yeah, I know. We don't want it recursive, right? We just want 1 of minus n, right? Yeah, like that. So we're writing it without recursion, yes. All right? So then if we were to do that same sequence, it's so annoying that when I copy and paste it, it reduces it back to 12. Now you could do it for lots of numbers. We only did it for a set of 5 numbers. But that's kind of a way that you can kind of check yourself. Okay. Peter, did you do this one in MATLAB?
Oh, this one I had to do.
You did by hand?
It's proof, yes.
Yeah. I know, I debated whether we should do this one in Maple. And I'm like, you can kind of see it. It kind of helps you. Maple can kind of help you. So when you plug it in there, you can see your output at least, and then you can think of your pattern. Okay. I'm trying to think how we could, solve it with Maple. All right. So see if you guys can do letter B without looking at the answer in the back of the book, right? C. Oh, wait, was that B? Oh, we did B. Yes, C. See if you can do letter C. Without looking at the answer, and hopefully you don't remember the answer. See if you see a pattern in there, and see if you can determine. Oh yes, we'll blow it up a little bit. Oh, before I do that, hold on. It's going to be great. Okay, cool. So this one is exercise 5D. The 5E. All right. So we have to remember our procedures, right? And these are for non-negative integers. All right. And so Maple actually does have a type that's a non-negative integer. It's called non-neg int. All right. So remember that when you're writing these recursive procedures, what do you put first in your recursive procedure? You always put your base case. Yeah, you always write your base case first when you're writing these recursive procedures. Because if you reach your base case, you don't want to go on inside of your program. Oops, I got to remember I'm in Maple. I always default to Java. Dang it. So then we return a 1. If n is our 0, that's our base case. Then we return 1. Otherwise, we're going to have another if statement in here to see if he is odd and greater than or equal to 1. So if n mod 2 is equal to what? He'll be odd. If he's equal to 1, he will be odd. And so we return our recursive call of 3 times our recursive call of n minus 1 Notice that that's how you write your recursive call. Now, do we have to check to see if n is even? No. Obviously, if he's not odd, then he will be even. So you could just write your else case. You don't have to write an else if. So we can deviate a little bit. We can say, okay, then we return 9 times our function call with n minus 2 as our parameter. And note that's what was given to us, and so that's how we figured out how to call a recursive call. And of course, we have to end our if. and then end our procedure. Make sure I wrote that right. All right, and then we can call our sequence the same way that we did before. And we can see if there's a pattern in here, which obviously there is. There we go. Yes, they're powers of 3. So how do they relate to n being 1 to 5? 3 to the power of n. Yes, very good. Okay, so, you can kind of use Maple to do these. Plus, it's just a good practice to kind of convert our logical statements into a programming language. Okay. And you could see how, it's a different way to kind of view this problem, maybe understand this problem a little bit differently by looking at it in a programming language. Good way to review, right? Okay, cool. All right. So most people got that, I hope. All right. I'm going to have you guys turn this into me as a class assignment. So we'll put it here inside of Blackboard. So I'll give you a couple minutes if you didn't finish your other couple of problems. You can finish them up while I make my assignment in here. And we do have extra class time. I thought we might have extra class time today, so I thought we could play our game again if you guys want to play our game again. And practice our recursion, playing our game. Cool. So we can turn that in after you guys are finished, of course.